Hello everyone. My name is Mahmoud, and I'm going to be presenting to you today a short paper that me and my supervisor published. This paper is about multiplicative, additive, and qualitative pairwise comparison. I'll just go through just the agenda. I'll talk a little bit about myself and my supervisor as well, Dr. Ryszard Janicki. I'm going to take a slightly different twist on explaining this topic, and this will explain kind of my background in terms of this. So I'll start first off with a scenario. We'll talk about evaluating the healthcare system. For me specifically, it's going to be in Canada. And then we'll start looking at pairwise comparison, both quantitative and qualitative. Also take a look at some consistency measures on weight tracking and determination. Towards the end, we'll look at an approach that is in the paper, which is doing combined pairwise comparison. And then there's an online tool that we developed to perform that method. So a little bit about my supervisor. So that's Dr. Ryszard Janicki. He's a professor at the Department of Computing Software at McMaster University. He published a lot of papers, specifically 170 of them, and co-authored 2 monographs. He currently, the latest monograph he authored is about concurrency paradigms. For myself, I'm actually I'm a student at McMaster University. Currently, I'm a tech lead at IBM working on Watson Orchestrate there, where we try to infuse some AI into automations. Okay. So we'll start first the scenario. So let's take kind of a step back and say, let's imagine that we're public health workers. And our aim or our goal is to assess the quality of the healthcare system that we're in. So maybe for us to do that experiment, we need to identify certain parameters or certain domains that we need to actually assess the quality of the healthcare system on. So let's say after discussion with some subject matter experts, SMEs, we decide that we have 6 parameters. We have effectiveness of the healthcare sector in improving the health outcomes. So if you get a treatment, does it actually help you live a better life? Access to healthcare service. A normal question for this one is like, how long do you need to drive to get to a hospital? Or how long do you need to walk to get to a clinic that you can go to? There's also capacity of the system to deliver appropriate services. So let's say, for example, you're at a hospital. Are there enough doctors or enough beds for patients to be in there? Safety of the care delivery, patient-centeredness of the system, equity in the healthcare outcomes and delivery. So with all of these parameters, us as researchers right now, we can take a look at them and say, okay, how do we assess the importance of these parameters? How do we say, can we, for example, equate that effectiveness is the most important out of these ones? If we start giving out some surveys, the results that come back, how do we determine, okay, which one is more valuable for us? So when we look at that scenario and actually trying to assess the importance of all these parameters, we come to look at this problem that it's a little bit difficult and mentally taxing to actually figure out the weight of all the parameters in one shot. Just by looking at all 6 of them, all 6 of them, which ones would be more important? So this exposes an old problem that dates back to the 15th century, which is you could actually compare the 2 domains or 2 parameters at a time, which would be a lot better than comparing all 6 in one shot. So for example, we can take a look at effectiveness in comparison to all of the other ones. And then based on that, we can establish a ranking of it. So this is actually where pairwise comparison comes in. It was popularized by Marquez Lee. I'm not going to pronounce the last name because I know I'm going to butcher it. It was developed by Faulkner and Ryszard. The modern version that we associate with doing this kind of pairwise comparison is the one that was popularized by Saudis and the PhD, the analytical hierarchy process. So with the knowledge of the scenario that we have, we'll go a little bit into a formal definition of quantitative pairwise comparison. And quantitative, there's kind of 2 sides of it. There's additive and multiplicative. I'll explain those a little bit later. So we'll assume right now that all of the parameters that we have, we're going to identify with this notation, which is EI, entity, and then whatever the parameter name is. So this is the set that we need to run. There's a quantitative relationship, and for now, I'm going to be assuming multiplicative relationship to be associated with them. So we'll say that it has the symbol EIJ. So this is referring to the importance of parameter EI to parameter EJ, where the greater the number of EIJ, the more important it is in comparison to the other parameter. If AIJ reaches 0, this means that both parameters are indifferent or we values are the same. So for a pairwise comparison, this is a matrix. For a pairwise comparison matrix, this is a matrix that contains all of these comparison coefficients, and we donate it with that notation there. So I'll go over to the next one. So this one is just explaining a little bit more about the quantitative pairwise matrix. The fact that AHP relies directly on having a quantitative matrix to operate on. This kind of exposes some problems a little bit later on, and I discussed in the qualitative pairwise comparison. So the pairwise comparison matrix that we can have can either be multiplicative or additive. And there's a formula to switch back and forth between both of them. For us right now, when we have the notation, it's AIJ, just as I mentioned earlier, it means that EI, which is the first domain, is more preferable than EIJ, and the quantification of that preference is the actual comparison coefficient itself, which is EIJ. Additive pairwise comparisons, you can represent them as VIJ, and the difference between additive and multiplicative, additive says, okay, the coefficients of the two parameters, if summed together, they will add to 1. That's the additive scale. So the one thing about quantitative pairwise comparison is they're useful if you actually have discrete numbers that are associated with the parameters in the domains. If you're able to establish that numbers, then it becomes good. There is a slight twist to this one, which is for some of the parameters that we discussed a little bit earlier, which is effectiveness or equity of the healthcare system, you can't attribute numbers directly to them. A subjective scale will be a little bit better to actually associate with these things. So we'll go a little bit into the next step. So with HP, it doesn't necessarily address the notion of having inconsistency within the matrix. So for example, right now we can attribute certain numbers or certain values to the parameters or the domains that we have. Once we perform that, we're not consistent in terms of, okay, do all of the weights make sense? Do we actually, me and you right now, do we attribute the same value to effectiveness versus equity? So the way we have it right now is we want to ensure that the metrics we provide are consistent. So the quantitative pairwise matrix maybe a little bit better, actually, quantitative, right now, if we want to look at the determinant consistency measure for the pairwise matrix that we have, we can actually look at each triad within the matrix. So we'll say, okay, from AIJ to AIJK, we would equal the coefficient, the comparison coefficient that we have between A and IK. So for example, if we're looking at effectiveness and equity and then access, we need to make sure that localized triad is consistent. So the way for us to actually calculate that, there is in 1993 by Dr. Ryszard, he introduced a distance-based inconsistency measure, and it's defined as this formula right here, where you actually take the most inconsistent triad within the whole pairwise matrix. So that's one aspect. And then after kind of ensuring that you have a consistent matrix and everything is good there, we can try to actually do weights and rank determination. So in order for us to do that, there's kind of two ways of figuring out the weights that are associated with the parameters that you have within your domain. So you can either do the calculation of the principal eigenvector of the pairwise comparison matrix, or you can do the geometric means of the columns or the rows, depending on how you want to do it. And the formula for it is there. Given that there's two methods of actually calculating the weights for small values of the consistency measure, which is the one we explained in the previous slide, the two methods produce very similar results. There's not that much difference between them. Okay. So with our knowledge of now quantitative, I know that you can have either additive and multiplicative. There's a consistency measure associated with each one of them, how to determine the ranking. Now comes the other aspect of this, which is to say certain parameters are actually subjective. There is no discrete value or quantitative value that you can associate to. this is where qualitative pairwise comparison comes in. In this scenario, it may seem a little bit more trustworthy to go with a qualitative pairwise comparison because we can say, okay, I agree with you that equity is more important or extremely more important than access, for example. So based on that, we get to actually attribute certain natural language words to the comparison that we have there. So in order for us to address the limitation of quantitative, we can use the qualitative matrices and they give us a more natural way. So we basically introduced kind of these set of binary relations that we can apply, and they do have a meaning, and the meaning for them is right there. So if you actually use the double table sign, it's A and B are indifferent of each other. So for us right now, I'll explain how we actually get to convert this qualitative into quantitative. But then we have exactly 5 relations that we specify. The reason why we went with 5, it's less mentally taxing. And on top of that, we don't want to start introducing this ambiguity into the calculation where, for example, you say if slightly in favor of equates to 5%, do we need to actually specify another metric or another word that says, oh, it equates to 2.5% in terms of the importance or the difference between them? So we have kind of 2 different relations right here. There's the ranking data and the ranking system as well, and the notation for them themselves. So in a paper, so actually it's not published in the paper for this conference, but it was in a 2018 paper. We have this scale right here, where you can actually convert from the qualitative symbols that we have over to either additive or to the quantitative, which would be additive or multiplicative. And basically, when you're doing the implementation for this one, based on whatever natural language phrase you associate with the parameters, you can actually pick the default or provide your own value there. Okay. So now that we understand both the quantitative and qualitative approaches, there is a way for us to kind of get the best of both worlds, where we say, okay, we have the qualitative approach, and there's this kind of methodology for going forward. We basically ask the SMEs, the subject matter experts, okay, provide me all of the information that you have using the relations that we specify. So that way they get the kind of, it's a more natural thing, they explain it, and then the matrix is then converted into quantitative pairwise matrix. The consistency measure is computed using the formula that we explained previously about the localized triad. And then we do the pairwise comparison using the formulas that Professor Kochbudai explained in this paper. The thing about these reduction steps to actually normalize the matrix, make it more consistent, it's to basically take the square root of basically the triads themselves and then nudge the weights bit by bit so that the whole pairwise matrix is consistent. After that, we can do the consistency measure. Everything is recalculated again. We can go back to the SMEs and say, okay, do you like these weights or not? And then keep iterating on the process there. Towards the end, this is where SMEs can come in and say, okay, I'm happy with the matrix right now. The consistency measure that is there is acceptable. And then we get to show them the weights and therefore the ranking. So, yeah, I'll actually show this one and then I'll jump into it again quickly. So there's a tool that we've developed for this one. So it's Pixel. What we've done for this one is trying to abstract away this notion of using the combined pairwise matrix comparisons. So there's basically 4 sections to it, and I'll walk through them in a bit. You get to, as an SME, you can actually jump in and use it. You can have certain parameters associated with it. You assign whatever relations, and then get to generate the quantitative matrix out of it, and then start actually doing the reduction operation and generating the weights and the ranking from there. So what we've done here is we've provided a tool for you to come in and actually start experimenting with it. There's a number of samples provided at the top, and then there's actually, you can go in and delete all of the parameters and your own specify the relationships that you want. For the sample that we were looking at, this was sample 3. So we see here that we have the effectiveness, access, capacity, safety, patient-centeredness, and equity. There is the relationships are defined here for them. And we can do the interpretation. So definitely this actually could be true. To actually have an actual equation there and then the symbol next to it. But right now you can actually get to put your own metrics in here and the relationships that you specify, and then we can choose to convert the matrix whether it's additive or multiplicative. So I'm going to go for now and say we'll have it as multiplicative. We do the conversion, and I see here that a new matrix is generated for me, and this is all using the default values that exist there within the table. So out of this conversion right here, I'm having this matrix. We see that the consistency measure for it is 0.64. For us right now, we're going to say that the default acceptance threshold is to have an inconsistency measure of 0.3. This has been proven to be an acceptable measurement. So the next step right now would be to actually reduce the matrix. Let's explain this. So we see that the matrix itself has been reduced. And right now we have a consistency measure of 0.26. And we see the weights for all of the parameters that we have. So based on the input that we provided in the qualitative matrix, we see, for example, that patient-centeredness is the most important thing, and that's what people value in terms of the quality of the healthcare system. Just a couple of side notes regarding this. What we notice, for example, the threshold, kind of the more we reduce it past 0.3, so just watch. So if we go to 0.1, we see that, yes, the consistency measure has reduced significantly for now 0.07, but the weights didn't change that much. So that's why we determined that, okay, 0.3 seems to be an acceptable inconsistency measure within the matrix. And the operation here, the implementation that we have, converges pretty quickly for a random set of inputs that are being provided. So usually it takes about 10 iterations, and then the matrix will be reduced, and then we can generate the weights out of it. Yeah, and that's pretty much it. Thank you.
Thank you very much. Are there any questions? Yes, please. Thank you very much. Thank you for your presentation. So I have one comment and suggestion and one question for you. So comment. Okay, your point of interest was comparison, but in the beginning you gave an example of evaluating the healthcare system. But evaluating is much more stronger notion than comparison. And by evaluating, you just assess and rank your system, how far or how near it is to your ideal solution. By comparison, you just compare with some distance or no. So comparison can be derived from evaluation, but does not hold vice versa. So one suggestion is you also get in your comparisons some levels. So look at the book of Professor Jozef Bujmo, which talks with computing evaluation logic. And you will find there a lot of very nice operators from drastic conjunction, total conjunction, partial, subpartial, neutrality, and mirrored all these junctions. So you will find very strong quantification of everything that you also mentioned here in comparison. So from my point of view, it's really a favorite book with his LSP method for that. And the question for you, you also apply here geometric mean. Yes. We have a lot of means: harmonic mean, arithmetic mean, power mean, exponential mean, and so on. And you must justify why geometric mean. What would you like to penalize, and what would you like to favorize in your aggregation of parameters by geometric mean? Can you analyze that? It's my question.
I actually haven't, no. Yeah, but this would be an interesting one to actually try. For us right now, it seemed that the quickest one was simply to go with the geometric mean, and it seemed to give us kind of a good weights for the ranking that we're in for.
The geometric mean is over the neutrality, yeah. And you feel means that are under neutrality. The arithmetic mean is just pure neutrality. Yeah. So you must decide which one and for what reasons.
Yeah. Okay, definitely, this will be a good investigation point. Thanks. And for the book you mentioned, I need to take the note. Yeah.
Okay, thank you very much.
Thanks.
Actually, when I was thinking about this, maybe it is related to the way you define consistency. Mm-hmm. Because it's this consistency is multiplicative, right? So maybe this is why geometric mean
is the best way to converge.
I can investigate that one.
It's also related to strongness of parameters. How much will each parameter will be influential? It's not the same in all these.
No. But yeah, see, as a vehicle for all study is the evaluation of the cost. So my question is, what if reality catches up with you and you have a paradigm shift like a home?
Yeah.
So what happens?
Then you need to make sure safety is there.
But I mean, some of the parameters may rapidly change, while I know they were right.
Yeah, yeah. But the thing about having the parameter there, like there's a natural attribution to it. So maybe right now in the time where it's COVID, we say, okay, that effectiveness or safety is a lot more important or extremely important. But the system here should be able to handle that, having that shift in paradigm.
Okay, thank you very much for your time.